So this is the syllabus, right? So you have floating point, right? Floating point meaning 4 problem types. So convert to IEEE, and then from IEEE back to decimal, back to binary. IEEE back to decimal, right? And then addition and multiplication, right? So hopefully you guys could do that, right? For floating point, I think we have revised it. You guys have solved what do you call it? Haven't you solved the practice problems?
Yep.
Right? And for floating point, you can literally make up an example, right? For floating point, you can literally make up an example, solve it, and then check your answer. Right? So you don't really need me to post something extra. I mean, all right. For performance, let's see. Did you guys go through the practice? Okay. So let me pull that up.
Yeah, just see. Is that's gonna be just like the practice problems? Like, or is it like the same difficulty?
Somewhat, I would say. Maybe a little bit easier.
A little bit easier than practice?
Yeah, a little bit.
Still the same amount of parts.
So I mean, it has to be doable in an hour, right? So calculate CPI, calculate execution time, that should be doable. Compare performance, right? But again, I mean, I have the solutions as well posted.
Where?
Right here.
Duplicate your screens instead of extending them.
Yeah. Okay. So let's open this way. Ooh. Okay, let me try duplicating it. So anyway, where'd it go? Right here. So now I can do this. Okay, there we go. That's good. All right.
Lectures. Did we cover lecture 12 on the test as well, or just lecture 11?
12 is control. So no.
No.
Yeah. Yeah. So, so the data path is covered. So all right. So consider 2 different implementations of the same instruction set architecture. The instruction can be divided into 4 classes, right? According to the CPI. So 4 classes of instructions. P1 is has a clock rate of 2.5 gigahertz. CPI is 1, 2, 3, and 3, right? So for 4 classes. P2 has a clock rate of 3 gigahertz. It's a weird room. Why is there a curtain behind and not a wall? So there's people behind it?
No, it's a beard. No, like a beard. It's a beard. Like you can probably see yourself. See if I've ever heard of the beard.
Oh my God.
Wow.
All right. Okay. Why they put a mirror in there? So it had, oh, so you watch yourself dance?
Yeah.
Okay.
Like in the gym, if you watch yourself work out.
Okay. All right. So we have 2 different instruction. The hell we have? We have 2 different implementations of the same ISA, right? Same ISA. And P1 clock rate is given, P2 clock rate is given. All right. So given a program with dynamic instruction count of 10 to the power 6 instructions, divided into the following classes. So 10% class A, 20% B, 50 C, and then 20 D, right? Which is faster. So in order for you to compare anything, right? Execution. So you have to have the execution time, the CPU time. So how do you get that? The first is class A, the total number of instructions, right? It says 10%. So it's going to be 10 to the power 5, right? Total number of instructions is 10 to the power 5. Class B, 2 times 10 to the power 5, right? 20%, 10% of the power 6. 20% of 10 to the power 6, right? So you have the number of instructions. The next logical thing to do is to calculate the time, right? Total time, execution time is CPI divided by clock rate times the number of instructions. So what we're doing here is 10 10 to the power 5. So class A. Let's consider class A, right? Class A is 10%. 10% of 10 to the power 6, 10 to the power 5. And CPI, we're having for P1, CPI for that is 1, right? So it's basically doing 10 to the power 5 times 1 times 1. Next, you have 20% for class B. So it's 2 times 10 to the power 5, right? Those many number of instructions times CPI is 2, right? Times CPI is 2. So that'll give you that. And then you do the same thing for all the classes, right? And then you divide it by, the heck you divide it by? The clock rate, right? CPI times number of instructions divided by clock rate. That'll give you the execution time. And all the formulas are given, and you should be able to, I mean, you can write them down in your sheet if you want, but they're already given to you, right? So you calculate the total execution time for P1, do the same thing for P2, and then in order for you to compare, you have to go with CPI, right? So as we said, CPI equals what? So it's going to be the total execution time times the clock rate divided by the total number of instructions, right? That's 2.6. That's 2.6. And then calculate the CPI and then compare, right? The CPI that's lower, clock per instruction. CPI that's lower, that's faster. So CPI of P2 is 2, so P2 is faster, right? All right, number of clock cycles. So number of clock cycle, basically this top part, right? Number of clock cycles is the top part, the numerator. So number of clocks are P1 for P2. You can calculate it that way. All right. Next, compilers can have a profound impact. So we've seen that two different compilers can generate different code, right? Different assembly code for the same C code. So compiler A results in instruction count of 10 to the power 9. Execution time is 1.1. And compiler B results in dynamic instruction count of 1.2 times 10 to the power 9, and execution time is 1.5 seconds. Find the average CPI. Find the average CPI for each program, given that the processor has a clock cycle time. So clock cycle time is given, right? So CPI equals, again, just plug it into the formula. That's all you have to do, right? All you're doing is plugging it into formula. So CPU time is 1.1. Number of instructions you have given, and clock period is 10 to the power minus 9, right? Nano, pico, hopefully you guys know that, right? All right, so you can calculate the CPI that way. The second one, assume the compiled programs run on two different processors. If the execution time on the two processors is the same, how much faster, right? How much faster? So when you say how much faster, you have a ratio, right? So number of clock cycles, find that out, number of clock cycles with the formula, and then you put in the ratio, right? There's really not much complicated here. All right. Number 3, a new compiler is developed that uses only 6 times 10 to the power 8 instructions and has an average CPI of 1.1. So what is the speed up? So first calculate the execution time. Execution time equals number of instructions times CPI divided by clock rate. So number of instructions is 6 times 10 to the power 8. CPI is 1.1. Clock rate is 10 to the power 9. So you get 0.66 seconds for execution time, right? And you already have the execution time for the others. Where the heck is that? you have the execution time is 1.1 and 1.5, right? So execution time is given. So you compare each. So you divide execution time for A with the new one, B with the new one, and then you know how much faster it is with respect to each one of those, right? So you have the formulas, plug in the values, and get the answer, right? For computer performance, it's that simple. It's not really complicated than that, right? All right. Which was the next one? Single cycle. So for single cycle, is it this one? Oh, by the way, you should probably go through this as well, right? The type of problems and stuff like that it's given right here. All right, single cycle. Okay, now I've said single cycle 4 times already. All right, so, okay, let's do this. Can you guys solve this problem? Instead of me just parroting it, try to solve it yourself. Open, I'll print it for you, but open the single cycle schematic, right? Yeah.
The ALU result, just the value of T1.
Yes, the ALU result is whatever pops out of the ALU.
Schematic be provided on the.
Yes.
Both like the symbol and multi.
Yes.
What did you say that you're gonna give us for this test? Like which diagram?
H1, and then the 2 schematics. MIP single cycle, multi-cycle.
Put that up.
The schematics, like the whole process, like the memory register file, whatever we, schematic, the
So the data path.
yeah, sure, yeah, data pack, yeah.
I did.
What? Oh, okay, what was this? MIP single cycle. Okay, there we go. But I mean, it's on Blackboard. You should be able to open it. It's on Blackboard.
You know, we don't need to do this. We just need to build the information.
First one, 5. Yeah.
You just have to add it, right?
Or it's a decimal, do the addition there, and then they're back in.
You can do hex addition?
It's a lot of work.
Okay, well, you can convert it. Binary.
Will we give choice off between binaries?
No, you can do it. Just the result, don't write the result in the 30 binary, right? The result should be in hex. You need H1? I think you need H1 because for the instruction format, yeah. Okay, let me open the schematic.
So basically, I was just like, I was like driving, there was like some of the slides too. I didn't taught myself.
Okay, so register destination, the value of register destination for add, right? Register destination mux is where? Register destination, it's right here.
Yeah.
So value for add would be what?
1.
1, okay, that's 1. The solution is there, right? But I don't know if I can write it here. Can I write it here? Oh my God. Okay, I just wrote it. Maybe I could, okay, 1. Ooh, it's like a caveman. Okay, ALU source,
Zero.
What?
ALU source. Okay, ALU source is 0. Why is it 0? Because you're gonna get it from read data 2, right? From the register. Because it's R type, not immediate. So this is 0. Mem to reg. Mem to reg. 0. Why is mem to reg 0? So we're getting the result from ALU and we want to push that to the register file, right? Register write. 1, right. I'm not gonna write it here, okay? The solution is posted. This is ridiculous. Mem read. Okay, why is mem read 0? Because we're not reading from memory. Mem write is also 0 because we're not writing to memory. ALU result? No. ALU result. So how do you calculate ALU result? Yeah, Dan. Well, yes, of course, but how do you calculate it? What is the caveat?
You have to sign extend T2 so that they're lined up properly and then you add them together.
Right. So 0, 1, 2, 3 ABC. Oh, this is a glass board, right?
0%.
That means sign extend, then write them.
And then
You
it's gonna be
zero. No, you sound. It's 30 ABC.
okay,
Gives you the best.
right? So you add them up.
There's a zero after the whole.
So if it's a 1, then.
Well, it is a sign extension. It's not a zero extension.
First number. First number. 1, 2, 3, 0 ABC. You just have 1, 2, 3.
Oh,
Then-
oh, look at that. They have a razor.
Because the T2 has 0, so you just go through with some.
Yeah, okay.
That's why. What?
This is 0, right? This is still sign extension, by the way.
What? Yeah, so the bottom number is not ABC involved. Do you want to affect the registration?
It's AAA. Who told me ABC? Somebody said
And
ABC.
then the top one, it's
The
ABC
top
on
one
the
is
top.
ABC,
maybe.
not 1, 2, 3.
It's like 1, 2, 3, 0, ABC.
You also wrote a 0 on the long row.
We still have to sign extend for.
Yeah, yeah,
Oh, one more 0.
Yes.
Okay.
All that.
Is that correct?
Yeah.
yeah. I mean,
Yeah, all right.
Yeah.
That's included.
Right. So it's sign extension because that is arithmetic. Right? Yes. Question.
That was good.
Oh, the answer for this?
Yeah.
Sure. We can do that, right? But you should be able to do it. You can convert this back into binary and add it.
Yeah.
Go ahead.
Would this be from left to right, 0, 1, 2, 3, 1A66?
Okay. Now, why am I just writing it down? Okay. So let's see, floating point. You have floating point.
Did you get 1? Get 1, 5.
I think that you can use your calculator for this.
Oh.
So let me see.
So
Let me see.
Fine, it is 1, 5.
Can I?
No, it's not an A there.
Yeah. The answer is whatever the addition is, but you can use your scientific calculator. Because I'm not testing you on anything here, right? So, number conversion, non-programmable.
We only have graph.
Sure, but non-programmable, right?
No, we only have the graph. It's good.
You have TI 84s,
Yeah.
Yeah.
so that's non-programmable, right?
Yeah.
Yeah.
So you can use that. Not the one that's like smartphone, you can download apps in it.
Oh.
Yeah. Convert this into binary or decimal and then add them. Because I'm not testing you on the addition.
Bro, when I write down when I write down the addition.
What?
We have to really have the result.
Yeah, valid question, but I would say that you have the calculator, you can do it.
How would you do the calculator?
Convert this into binary, and then add them up.
How does the calculator help? They're pretty big.
You can at least convert the numbers.
In binary?
Yeah.
I don't think.
That's not.
There's a way.
I mean, you can.
There is a way, right?
Can do it manually, like doing 12 times two. Like, it's one.
Okay, fine. You have a calculator if you want, you can use it. Otherwise, you should be able to do it manually anyway. Right?
You got it down.
All right. Yes.
Is there gonna be like conceptual questions like there was last time, or are they all gonna be like applications, but
Conceptual tends to be like what does this mux do? Right? So we've seen that in the class. So I have a question. I think for one of the practice problems, I have a question conceptual. So all right, now question 2, who can answer that? Will the following instruction work given the 2 faults, but you have to consider only one fault at a time without the other fault? So the instruction is subtract. The first fault is race to destination mux is fixed to a value of 1. Race to destination mux, this mux is fixed to a value of 1. All right, will subtract work? Yes or no?
yes.
How many of you say yes? Okay, very good. All right. I don't know it's wrong. So subtract, race to destination is 1, it will work. Look at the F1 h1.pdf, right? Memwrite question. Oh yeah, memwrite 1. If memwrite is 1, it would not work. The subtracting, why? Yes. Yes. So the answer is not Boolean. Okay, it says explain your answer right here. So you have to explain it, right? But when you say explain it, don't write an essay there. 1 or 2 sentences, right? Because I have to grade it. Yeah.
Is the answer then, yes, it still works, but we'll write it in memory?
Yeah.
Or no, it doesn't work because it's.
No, it's gonna work because the subtract doesn't use memory, so it's still gonna work. You're gonna write something in the memory. You're gonna write the result of that subtraction in memory. Well, at a random address, by the way. No. Okay. Can you tell me what gets written in the memory? No. Okay, so let's make it interesting. This problem, memwrite is 1. Okay. Right here, memwrite is 1. What gets written in the memory for this instruction? This is the instruction. Subtract T1, T2, T3. Subtract T1, T2, T3. What gets written in the memory? T2?
The data from T2
Okay, data from T2 is getting written where?
into the subtraction.
Subtraction. Right. Yeah, that's correct. So the data from T2 is fixed to the right data bus. If you make memwrite 1, then that data is written and the address is the subtraction of T2 and T3. Right? So memwrite. Okay, memwrite, memread, register write. It cannot be don't cares. Right? They have to be either 1 or 0. Right? Because they're protecting the components and stuff, so they have to be 1 or 0. Everything else can be don't care. Right? What we're doing right here. Okay, questions? Jump?
Yeah, doesn't that have a don't care on the memory?
No. Memory read and memory write and register write should not be don't cares. You can put them all 0. Let's go for the next one. Where is my web page? Right here.
I was gonna say, is there anything in the slides that might come for any critical paths?
Critical path. So that one is that was one in the homework, right? In homework 6. Let's go through that.
It goes.
So- So when you're calculating the critical path, right? When you're calculating the critical path, so what do? So for example, you have IF stage, ID stage, EX stage. So for IF, you're doing what? By the way, that question was multi-cycle.
So.
But IF does what? PC gets PC plus 4. So that's one path.
So that's why it doesn't affect.
Another path is going to be MDR,
Zero value.
not MDR.
I'm just wondering.
IR gets
Right.
memory PC. So that's another path, right? So you have to calculate the delays for each of these paths, and then you consider the worst case delay from them. Right? Same thing with EX. I'm talking about the homework problem. The homework problem on critical path, right? So calculate the delays for each concurrent path, and then can take the worst case path. And you do this for IF, ID, EX, memory, write back. And then the minimum clock cycle time would be for load work, but the latency for the instruction would be which of these is worst? Is it IF stage? Is it ID? Is it EX? Whatever, right? So max of IF, ID, EX. I think then the first one was R type. So for R type, you have write back. So max delay for each. Yes.
Doesn't it depend on the instruction, like the execute stage is not bringing the same amount of memory?
Yeah,
For every.
it depends on instruction. Yeah, yes.
So you have to calculate those numbers, like.
So if I ask you, if the question is R type. So for R type, what is used? You're using the A equals. You're using the B equals. You're not using the target equals, right?
Yeah.
The target equals only applies for branches. It's still calculated, but we don't need it,
Oh, I see.
right? We don't need it for individual instruction type latency. We need it for minimum clock cycle, but we don't need it for individual instruction latency, right?
Is it not? But the answer is always memory access if memory access is.
Yes, usually it would be either IF or MA.
So, okay, so typically what we can see is.
Yeah. So if I were a student, if I were trying to save time, I would just calculate it for IF and MA and then run with it. But make sure the EX stage doesn't, what do you call it? Trick you. Right? It shouldn't, because memory is and should be the worst delay. ALU should not be higher than memory. It's typically not, right? So I would just calculate it for IF and MA stages, and then that would be which one is the worst, take that. That would be the latency. Right? Okay, which is the next one? MIPS single cycle multiple choice. So this one doesn't open, so
Yeah, we're gonna have multiple tests.
what?
There's no
It's for practice.
correct?
Multiple choice? Yeah. Which is why I put it,
Yeah, it's a practice or yeah, it's a test.
it would be on the test. That's why I put it in the practice.
So how many questions do we study?
The three points syllabus that you sent us. It's
Hold on.
like 34 points, 40 points. 60. Where were them?
Which one?
Oh.
Like where?
Okay.
Choice question.
Oh, multiple choice of question type. So this is so single cycle and for single cycle and multi-cycle. Unless you guys don't want multiple choice. I mean, that's what I thought.
Still, how do you resolve this?
Okay, I can't hear you. What?
Is the multiple choice part of the three problems or just one of the problems? Part of the.
Part of the three problems.
Part of the,
Yeah.
each one has like.
Each one has an each part.
So, all right,
In an hour?
all right.
Plus 2, 8
So MIP single cycle. MIP single cycle. What is the primary purpose of data path in a processor? Yes. Okay, move data between components, right? That's correct. So it's gonna be this one. How do you answer that? Red. All right, which of the following is not a component of the data path? ALU, register file, control unit, or instruction memory? Yes.
Control.
Okay, control unit. Which instruction type requires register write signal to be deasserted? Okay,
Or.
yeah. Add. Okay, somebody else answer. The mem read, no, it's good, but I just, I'm just saying. The mem read control signal. What?
Reg, so you said reg right. Wait,
They're
it
all.
has to be zero, right? Is that the question? The question is it has to be zero, right?
Oh,
So which instruction type? Okay, why did I remove everything? So which, hold on. The register write signal to be deasserted. Then that was the wrong answer. Yeah, it's store word.
Why is?
So register write. So let's go back to the preview. So right here, register write is here, right? If register write is 0, what does that mean? It means you're not going to store anything in the register file. You're not going to store anything in the register file. If this is 0, then nothing gets stored in the register file.
What's it between write data and register write data and memory?
This one, this write data, you have the data there, but to actually store it, you have to make register write 1.
What's it between memory?
In memory, if you want to write something in the memory, if you want to write something in the memory, mem write has to be 1. So for example, let's say you're running add. Let's say you're running add. So what happens? You have two registers here, and ALU adds them, and the result, so you select 0 here, and that has to be written back in the register file. For that, you have to have register write 1, right? So for add instruction, you need 1. For load instruction, you're gonna have the address here, load the whatever the data is at that address, goes through mux line 1, and it has to be stored back in the register file. Again, you need register write 1, right? The third instruction is ADDI, which is obviously you have an immediate, you have one register, and then you have a sign extended immediate value. Again, that has to be stored in the register. For store word, though, the address is calculated here, the data comes out of here, and you're writing in the memory. So you're not writing anything back in the register file. So therefore, register write can be 0. So the mem read control signal, wait, the hell? Okay, which instruction requires register write to be deasserted? So I would say that store word. Right? Yeah. All right, next one. The mem read control signal is asserted for which instruction types? So mem read controls if the memory can be read or not. Which of these instructions you're reading memory? Reading memory. Okay. Because you're not reading memory instead, you're storing it in memory. So you need the memory write to be 1.
No, put it on your sheet.
Right? Memory read is asserted, that means 1. That means you have to read from memory. And that only happens in load word, right? If a designer accidentally set mem to reg equals 1 and register write equals 1 for an add, okay. A really complicated or easy problem, depending on how you see it. That statement didn't make any sense. So if a designer set mem to reg, where is mem to reg? I think this, yeah, mem to reg right here. So mem to reg is here, is 1, and register write is 1. So register write is 1, but the instruction being executed is add. All right. Register write 1, it's fine, no problem. mem to reg is 1, what happens? You're running add, right? Instruction is add. Either you're adding two registers or you're adding a register and immediate value. Okay, so can I write here? Maybe. I don't think so, right? Okay. Okay, this mux. Focus on that mux.
Would be the second. What was it?
The question is, if a designer set mem to reg mux 1 and register write 1 for the add instruction, what would actually happen? So one is add would execute normally. Okay, register would be written with the data from memory unit instead of ALU.
Yes.
Okay, that's correct. The instruction would be rejected by the control unit. Right. The processor would crash. Well, not in this case. Right? So option is this. All right. 6, in a single cycle data path, if we trace path of data for load word, which sequences correctly describe the signal flow for load word? So it's going to be PC, instruction memory, we're load word, right? PC, instruction memory, register file, ALU, data memory.
Yeah.
So wait. Back to the register file. Yeah. So there's only one thing that ends in, no, there's two options. So one is this and another one is this. But the first one is correct because we have to start at instruction memory. So, all right, let's go to the next one, right?
Not us.
ALU function is fully determined by just the opcode. Okay, false. Right, yeah, for the R type. So if reg write is stuck at 0, which instructions fail? So let's go back. Reg write. If reg write is stuck at 0, which instruction is failing?
Add.
This one? Not store word?
What? No.
That question's not.
If register write is stuck at 0, which instructions fail? So the answer is this. If well, they will not execute, right? Because all these instructions need you to write back in the register file.
Wait.
Technically.
So SW you don't need to write back. For branches, you don't need to write it back, right? So which instructions fail? The only instructions that fail are these, right? If mem to reg is stuck at 1, which instructions fail? Mem to reg is this mux, right? It's stuck at 1, which means it's taking output from memory and writing it back in the register file. So which instructions will fail?
What do you mean? Because adding sub, I guess, I mean, they also give us one, but it doesn't, so it still functions.
No, it can't function because for add and sub, the value, the answer is here in this line.
Yeah, but it'll still give you like an add.
That's not useful. Add and sub.
I'm asking what is fail? Like, it still
Fail-
functions, but it doesn't function how you want.
Okay, when I say add, what needs to happen? So add $T0, $T1, $T2. So T1 and T2 has to be added, and the result needs to be placed in T0. Okay, Jamie.
Yes.
So T1, T2 adding and place the result in T0. If it can do that, then it will succeed, right? What determines single cycle clock period? This one should be doable. What determines single cycle clock period? Right.
Yeah, we get.
All right. So let me save that. And I'll upload that to the Blackboard later. All right. Next. Right, multi-cycle. Okay, this one can't zoom. So let me open that here. All right. So explain the inputs for PC source mux. Write down the instruction that use these three individual inputs and indicate the cycle in which they use them. All right. Can you have a laptops open the schematic for single cycle? Multi-cycle. Okay. Open the schematic for multi-cycle. And for option 1, PC source input is 0. Right? Look at the PC source mux on the right. And tell me which instructions use that. And indicate which cycle. Is it IF, ID, EX, memory access, or write back? Yes.
It'd be like the first one, or if you look at the answer, you like the first.
Answer.
The first one, it's like PC plus 4, so that's our type.
PC plus 4. So maybe I should write here. Okay. Okay, so PC equals PC plus 4, right? Which instructions need that? R type? What about load word? I type? So we have R type, we have I type. Which else?
Jump is
Yeah, but it goes right there.
Look at, okay, I need to open it then.
two is. Oh, I guess.
So this one right here. So that's connected directly to the ALU, not to ALU out temporary register, right? It's connected directly to ALU. What does it do? It does PC plus 4. All instructions do PC plus 4, right? All instructions will do PC plus 4 in the instruction fetch cycle. So the answer for that is all instructions. Where'd it go? Right here. So this is answer is all instructions.
Wait, how is that the case?
Right? What? Next one. PC input, PC source input 1. Branch, right? So branch instruction uses that. Which cycle does it actually use it? Branch doesn't access memory. Branch, so branch, what does it do? IF, ID, EX. That's it. So EX. So this is going to be branch. Right? PC source input 2. PC source input 2. Yes.
The IDs.
Which one?
For input source, or for input 1.
Really? Which is this multi-cycle? Oh, wait. Multi-cycle key. Branch instruction used to branch at label cycle 2. Well, I don't think it's used at cycle 2. This is incorrect.
So
Hold on, let me think. So let's go back to the PDF. So what happens? So in the IF stage, you have PC plus 4. Then in the ID stage, so hold on. In the ID stage, what happens? You have the branch target being calculated, right? And then to actually branch there, hold on. To actually branch there, you have to do what? You have to look at the 0 flag, right? To actually branch there, you have to look at the 0 flag, which is wired here. right? So the PC write conditional is 1 for branch, PC write is 0. That means that only if the 0 flag is set, then you're going to branch, right? So when are you actually going to branch? And what the hell was the question? Write down instruction that use this individual input. Okay. So for this mux, BEQ uses, it's a weird question. When does it actually use the mux? Is it ID? Is it EX? I think, no, I think, no. I think that it's calculated in the ID stage. It's calculated in the ID stage. No. Hold on. So you already have the calculation done here, right? And in the EX stage, what happens? Because there's a temporary register here that you have to cross. So even though the calculation happens in the ID stage, because of this temporary register, you're gonna have to go to the EX stage to actually output this here to 1 and then be stored in the PC. Right? Because that's why we said PC plus 4 uses this line, right? Because it happens in a fetch cycle, right? In instruction decode itself, it's being calculated and then it will be stored in the temporary register. Not PC plus 4, the branch target.
He's technically right. Calculating the branch in the ID stage.
It
happen until you happen.
Yeah.
On the test, which one would you want to put? Will we get points?
So-
for ID? We put EX.
No. No. It's EX. Yeah. Yeah, I prepared that answer key in a hurry. All right, which is why we have a review session.
We studied that stuff before here. We studied the wrong stuff.
He like just posted them.
Yeah, I just posted it 5 minutes before.
Oh.
Okay, let me do this. Let me go ahead and delete those. Multi-cycle key. All right. Single cycle. I think performance is fine. Multiple choice, we solved it. And the multi, hold on. Okay. So I think it happens in the EX stage here, right? How do you write? Why? Okay. All right. Delays. The delays in multi-cycle MIPS are given below. So a program has 100 instructions, the following mix. So you have R-type, load, store, branches, and jumps. What is the minimum clock cycle time of this processor? So you have memory delay, ALU, register file, register setup, and register read, right? Yes.
Isn't it just gonna be the memory access, whatever that path is?
Yeah. So this is multi-cycle. So you calculate it for IF
Yeah.
and MA, and then see which is worse.
Is it not HMA?
It's IF.
Oh.
Yeah, but calculate IF and MA because they both use memory. And as you can see, memory is clearly 300, right? So yeah.
Two questions.
Mhm.
First, can you post the solution homework 6 so I can actually see if like I did the math right?
Yes. Yeah, I'll do that.
On the exam, like, let's say you were to find one of these things, if I just did IF and MA for the ones that you.
That's fine.
Effectively, that's okay.
Yeah.
All
IF and MA, so you have to look at memory delay. Memory delay is always several magnitude of times more than ALU. So if you have anything that accesses memory, it's going to be worse anyway. Yeah, IF or MA. Yeah. Yeah. Yes.
I swear that's not correct.
Where?
Please.
I think you skipped PC source 2 for the first one.
Like on top, yeah. PC source input 2 is for the jump address.
I think your explanation was supposed to go with input 1. We didn't do input 2 yet.
Oh, okay.
Yeah.
So we still have to do input 2. So, all right, PC source 2 then. What happens in PC source 2? Hold on. This is the wrong one. PC source 2, it's right here, right? So for jump, what do you have? You have IF, ID, and EX. So for jump, you have IF, ID, EX. So it would have to be which stage? No. It can be ID, it has to be EX. Right? So for branch and for jump, it's EX, right? Where is the other PDF? Okay, perfect. I'm thinking for the first exam, the review session was much better, right? What?
This is a very applicable to the exam, except they're simpler. So I like we're going over it.
Okay. What?
I like, yeah, I just let me actually hold on to now.
Last time he had it, he gave us like.
We have more information on what the questions are going to be. Then just, I mean, we have some delay.
That's why we're going. What? That's what we're going through. That's what we're going through. The type of questions. Yeah,
Can we do like one like latency problems?
sure. Which one?
Actually. I don't know.
That's what I was doing here. That's what I was solving here for multi-cycle, right? So for multi-cycle, the latency for you to calculate. Okay. That's what I was doing here for multi-cycle. If you consider R-type instruction, right? So if you want to calculate latency of anything, right? Usually the memory, anything that touches the memory is going to be worse, right? Which cycles you're reading the memory? IF and memory access, right? So for R-type, you don't use MA. You only use IF. So that means that you calculate the delay for PC plus 4, right? Now, given the parameters, you have memory delay. ALU is 100. Register file is 50. Register setup is 25. And register read is 20. All right. All right, so for PC plus 4, and for the question that I put, you have to consider the delay. So memory, anything that accesses memory is 300. Register file is 50. Register setup and register read applies to all registers. All right, register setup and register read applies to all registers. That means if you're updating PC, you do register setup. If you're reading from PC, you do register read, right? Applies to all registers. So now, PC equals PC plus 4. So you want to read the register first. Right? So
Question. Didn't you say that reg read never applies to the program counter in the homework?
that was for the homework because it's
But it's the
specified.
same- It's the same data.
Yeah, but this homework specifies special conditions in the paragraph.
Okay, so.
So there's no
We're just
conditions.
arbitrarily saying when it, like, which delays matter.
No. For the data path, right? If nothing is given, then register setup and register read applies to all registers. But the homework has special conditions that you have to consider when you calculate them. And so that's why we said register setup applies to what? I think it was RF or something.
I don't know.
Yeah, they had that two sentences for when register setup and register read apply. Right? But what I'm saying is, for the problem that I have put here, you have register read and register setup for everything. Any registers, you have register read, register setup. So you're reading PC. So register read. Right? You read the PC, it goes through what? It goes through the mux, right? Mux delay is not given, so there's nothing. And then the ALU. ALU is going to be 100. After the ALU, it goes through that mux again, but mux delay is not given. Then you have PC write 1, and then you're storing it back in PC. So register setup. Which is 25. Right?
Do you use like the pencil feature on the thing, like draw what you're looking at and like tracing through?
Pencil?
That'd be really helpful. Like use like the highlighter and just kind of like go through where you're looking.
So PC.
No, not that. It's no.
It's this.
Okay.
You have 4. Okay, what? And then it goes through here. 0. Back in PC. Yes.
It's just that.
Yeah, but not just fetch. It's for this part of the fetch.
That's
Yeah, and then you have another line that reads the memory pointed by the PC and stores it in IR, which is the instruction register. Right? So what has to happen for this? Again, register read 20. Then you have memories. So memory delay is 300. Right? And then instruction register setup.
Can you use a different code?
Yes.
Thank you.
So you calculate that and you consider the worst delay for this. So for this path, how do you change the color? No, I don't want to do that. Okay.
That's all in math.
Yes. So this happens, right? And then this happens.
So I shall stop at the
Yeah.
Okay. And that happens for every instruction.
Yes.
Okay.
Every instruction.
Yeah.
It's like you do ID and then EX or just.
Well, you have to work, so if you go look at the table, it says memory delay is 300, right? So if memory delay is 300, that means that anything that accesses memory is going to be worse. So you calculate it for IF, you calculate it for MA, memory access. R type doesn't have memory access, right? So IF is enough for us. Right? But if you want, you can go and calculate the other delays as well. Yeah. So what I'm saying is, if you compare the delays, The memory delay is 300. ALU, which is used in ID and EX, right? It's only 100. So anything that touches memory is going to have a worse delay. Any stage, right? IF, ID, EX, MEM, and write back. Out of these 5 stages, only IF and memory access touch memory, right? Yes.
Is the memory delay like what is that? If a stage is just writing to memory and not reading, does it take the whole 300 still or?
Yeah. Memory delay, anything that accesses memory or reads or writes from memory. Yeah. So IF and MA will have memory, will touch the memory. They will have worse delays. R type doesn't use memory, right? But if you're doing for load word, then you have to look at what it's doing, right? So during memory access for load, anyway, is R type clear?
No. But so that's our type.
Yeah. So this one, this has 300, so you calculate that. So it's going to be 345, right? Yeah.
Are you sure it's mem for the instruction decode? I think it's registered.
Not decode. This is only IF.
Oh, what this?
I thought you said our type didn't have mem.
He's doing.
Well, you have to read the instructions.
Oh, you just wrote it underneath.
Yeah. So this is the same thing happening in IF.
Put a line.
Yeah. So you have to compare them.
These are two different options. They both have to.
Yeah. No, IF.
I know.
Oh, wait, yeah.
So those are two different options.
Yeah, like the parallel paths.
So both of them don't happen in every one of them. Like our type would only use the left one and not the right.
No. This is IF. IF and ID is common, right? We
Our
need
type
the
doesn't use mem though. So.
You said you said.
MA during MA. This is IF stage.
Oh,
It's during a certain stage.
Okay, so
I have uses.
they're both happening at where they want either one of them.
I have an ID.
So
Yeah.
so this delay, 345 delay is applied for R type. Store word. No, not store word, not store word. R type, what is the evidence of branch, dump, and R type, right? For load word and store word. You just have to check the memory delay in MA.
So say it's over, the IF will most likely be the longest in most.
It would most likely, but you still need to calculate the.
But
you
for
know,
those
for-
two specific instructions, every other
Yes.
instruction.
Yes.
IF.
Yeah.
Can we go through and load word and W and MA?
Yes, so for load word. Okay, we need a different color. So for load word, what happens? So you have register file, RS, and offset being added in the ALU. ALU output is stored in ALU out, which is the address. And after that, we have memory access. So memory access, you do ALU out, right? ALU out, so register read. And then you're going back to the memory. Oh, let me draw it. So that's one path. Right, that's one path. Green. Another path is this. Oh my God. Green doesn't work. Okay, let's try this one. Okay, we don't, which color should I use?
Oh, orange. We went back, the mouse at one.
Okay, orange.
Mouse is one.
So you have this line. And that goes here, right? So for memory access, for load word, wait a minute, the hell? For store word and load word, right? For load word, this doesn't apply. For load word, this is it. So for load word, you send an address to the memory, and then the memory will then fetch the data at that address and then store it in MDR.
So it's reg read, it would be reg read and then that's memory.
Yeah, not reg read. Yeah, reg read. Reg read and memory. So, I mean, IF is going to be worse. IF is still worse.
So why is he using the register part when it doesn't go to the register file?
No, 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 not RF. RF is register file. So any register, right? So you're reading ALU out, so there's a register read.
Oh, so you're reading a register.
Yeah,
So you read setup and read read in both cases?
for all registers. And if it's going to be for RF, then you use RF delay, even here 50. So for load word, it's going to be like 320. Yeah, 320. Right, so for load word, it's going to be read read and memory. Right, for MA. For store word, we have only one additional thing. Hopefully this is orange. Oh yeah, it is. Okay. For store word, right? For store word, what do you have? You have the path from reg read and memory again. Right? Two paths are the same. But for store word, okay, let me do it somewhere else. I don't have space here. Go right in. For store word, you have two paths. So path 1 and that's path 2. Path 1, path 2, right? Path 1 is going to be reg read. Yeah, the one in the blue and the one in the orange. No,
They take the same time.
they should, but they take the same time, yes. But I'm just calculating this, yeah. So path 1, path 2, we have race to read and memory. Again, you have the same thing, race to read and memory, right? So it's going to be 20 and 300. So for both, it's going to be 320. So 345 is still the highest, right? Yeah. What mux?
I'm looking at that web.
Yeah, but there's no delay for mux.
Oh, and that's, yeah.
Yeah.
We actually.
Are we gonna have a situation where if this is wrong on the exam, like
I
it's
just said-
that will not miss certain thing?
What do you mean?
Like, you know how you said before that reg setup wasn't applied to everything?
That was for the homework problem because they had some specific limitations.
Okay.
For-
Limitations on the.
No. It's going to be yeah, something like this.
This is that's memory access.
Yeah. So this
What's
is
the line in the middle of fetch.
the two paths. Yeah. Two paths, and you have to compare, find out which one is the worst.
Well, you might as well. Why not? Why not?
Can you just like make the whole chart of everything?
Of what? I just did.
Oh.
You have IF stage, only two stages access memory, right? IF and MA. R type, branch, and jump does not use MA. So therefore, this will be the worst delay for that. For
Worst case in every scenario.
yes,
Except for loader.
except for load word and store word, in which case, well, yeah, you're right. But I'm calculating it just for the heck of it, right? And because it uses memory, right? And so, but we find out that it still works, right? Yeah, I should probably have eaten something. I didn't eat anything.
That's right, load word is just the.
I was literally considering something.
This is.
Okay.
I must use.
For this one?
And then it's
I don't think we should change the test last night.
That's what I'm saying.
I think I did. So just.
I haven't.
Go through on there.
Oh,
It's for credit, guys, this,
It's like backup status.
I'll try to have an extra credit question.
like.
Like a bonus question, like 10, 5%, 6%. Yeah,
The same thing, or is it gonna be like random sports?
same material, same syllabus. right? I don't want to change anything in the last minute. It's not really good. What?
First question would be, what was wrong with that? I mean, yeah, everyone remembers that. That'd be a good one. You don't want to be paying attention.
Question, yeah.
There is multi-cycle or there's not?
Yeah, I'm not changing anything right now. Just whatever it is, let's just keep it that way.
That's better.
Let's just go to the last one. And then if you have any other questions for some of the problems, let me know. So we have, yeah,
What's the? We get a path question for single cycle and a control question. As I was like looking through the data path slides, I think it was fairly similar, correct?
yeah. So let's go to the data path. Hold on.
Like what it feels crazy.
So for example, for this question, this is a control question, right? This one is also, I would say, control. Yeah. So for data path, I don't know. There's specific questions for data path versus. Yeah. I think so. Okay.
The difference between a control and a data path question, or just those two? He said it's mostly control.
Yeah, but let's see what data path. I mean,
It would just be tracing the data path, right?
Yeah.
It's a question like we're doing from the cycle.
Yeah.
And he gave us those in class.
Yeah, we have those diagrams.
Okay.
Thank you.
All right.
So you're saying we have to actually trace the diagram with a pencil?
No, but you should know what each mux does, for example.
I mean, for single cycle, we do it in box.
Yeah.
Just remember, we have more information on single cycle than multi-cycle.
And it is worth more.
It's worth more, okay, good.
No, it's worth a lot more.
So it's worth 40% versus multi-cycle for 25.
Okay.
That's all, that's all.
Okay. So last question. Here's what I'm gonna do. All right. What? A? Yeah. Yeah. Can somebody take a picture?
What?
Take a picture of this.
I'll let you know. Are we done? Set it.
So is I.
Set it, are we done?
Yeah, unless you have questions. Yeah.
Yeah, so in like this table, if we have like, so like this RF means we have the register file done.
Yeah.
And then it would be like reading from that, I guess just kind of like interpreting like this.
So what was the question again?
Just like kind of like what's going on here in terms of like delay. Like if we're basing it on like these delays.
What table is this?
This is just like the decode for like anything.
He has the answer.
Like
Multi-cycle, right?
yeah, sorry.
Oh, but is it right though?
Let's see. Multi-cycle 11. Thank you. You too. So this one, right?
Yeah.
So what's happening is the A, right? The temporary register A is getting stored with the data from a register
Yeah.
pointed to by the instruction memory.
Yeah.
So basically you have stuff like instruction memory, IR read.
Okay.
So register read, it's a register, right?
Yeah.
The register read, then RF delay, and then register setup.
And it's the RF delay because you're going into the RF.
Anything that touches register file will have RF delay.
Good. Got it. Thank you.
All right.
For the jump, the decode, since it's like not actually have anything that you're like decoding, do we just kind of skip it?
For jump?
Yeah, for instruction.
No.
Or
So
does it just do it, but it doesn't really like have a path? Or how does?
for multi-cycle, right?
Yeah,
So considering the delays, you have IF delay. For ID stage, it's not, it's actually decoding the instruction.
okay,
Because once it decodes the instruction from the control, then it will assign the control signal to the mux.
okay, so it's control,
Yeah, but we haven't covered control.
yeah,
So yeah, IF delay would be the worst.
yeah.
Yeah.
I was just wondering for.
Okay.
So when it comes to like mix being pipeline,
Mhm.
so that like
Yeah.
did that significantly change like the processors like design?
Not the design. So for pipelining, what happens is usually you have one instruction being fetched,
Yeah.
right? And then the previous instruction is being decoded, and the two instructions back is being executed, right? Depending on the number of
It's
stages.
like, that's a 3-stage, right?
Yeah, that's what I'm saying. So like in pipeline,
Like implementing that on this, like.
so I have, then
Yeah, I'm gonna stay.
ID,
Yeah.
you have here. Here is. Now we're going Right now,
That's,
Yes.
If anyone has a compassion, I have like really keep showing information that I can.
That'd be a 3-stage, but so far we have.
But if the pipeline is full, you have 5 stages. So if the pipeline is full, the numbers change. If the pipeline is full, then you
Oh,
have-
is the pipeline not variable?
It's
all.
No, it's not full yet. So let's add ID. It's nothing here, right? So hold on a second.
What
ID.
color? One color, it's on the left.
ID here, then you add IM.
I'm not using color, I'm doing it on.
Then
black and white.
you have-
That's crazy.
Wait,
What, the pictures with the tats on it?
Yeah.
That's
I thought like when people say, oh, it's like a 2-stage like pipeline or
okay,
3-stage.
pipeline, the classic example is, let's say you have to plant trees.
Yeah.
So plant trees mean what?
I'll be buying around like 9.
Yeah.
Plant the tree, and then cover it.
God. And-
So-
Yeah.
Normally what will happen, one person will dig, right? And then the same person will plant, and the same person will cover. So it's like 3 seconds, or 3 hours, or whatever. If it's pipeline, one person can dig a
The
hole,
actual thing. you don't
then
see the
he will
screen.
dig the second hole.
They also-
Meanwhile, person 2 can plant.
Yeah, right.
Then this guy will dig another hole, well, this guy will plant, and this
Well,
guy
I
will
got
cover
it.
it.
Yeah, got it. I got that.
So after the pipeline is full, it's gonna be one hole being planted with a tree per hour or minute or whatever.
I get it. Okay, but you call these individual things like stages?
Yeah.
That's what we call it.
Yeah.
But implementing these, oh, like, so then the.
So
next
you would have to modify it because you would have pipeline registers in the middle
Yeah.
that store.
Is it significantly modifying this? This would be like 1 stage technically, right?
No. For pipeline, you'll modify it because you insert pipeline stages in the middle,
Yeah.
I've done half.
right?
This is not pipeline.
No, it's not pipeline.
Yeah. Oh, I
So
thought
you have to insert separate registers here.
I thought another term for like non-pipeline would just be like a 1-stage pipeline because like it like one person just has to do all this stuff.
Yeah, well,
Yeah,
yeah,
okay.
non-pipeline is one person.
Okay.
Yeah.
So this is gonna be like significantly like altered, right?
Yeah, because we need separate registers here, right?
Yeah.
Because we have to remember the outputs from the previous stage, also the control words from the
Right,
previous
gotcha.
stage.
And that like newer iteration of the CPU that will be on the final.
Yeah.
Okay, got it. Just
Mhm.
wondering. Thank you.
Okay,
Are you, keep us a homework 6 answer key?
yes, I'll post it in
Okay,
a bit.
Thank you, that's.
Yeah.
that was-
I-
my- You go first.
There you go.
With like for me, it's like the thing I have, I understand what this is. I
Okay.
understand like the concepts, but the hardest thing for me is actually tracing it on the chart itself.
Okay.
So do you have like, what's the best tip to actually understand that? Like just go through the slides again or?
What do you want to trace?
Of
multi-cycle,
like if
single
I was really told to trace anything, I'd be, unless single cycle, I kind of understand because of the lab or I have
Okay.
to actually like design it, but for
Okay.
multi-cycle, I don't, I literally just figured out now that you do multiple like actual loops through it.
Oh, for calculating the delay.
Yeah.
So-
So like in general, like if we're gonna be asked a question on it.
Yeah, in order to calculate the latency, like.
So for latency, I already gave you the answer, right? So
Yeah.
you have IF delay and MA delays.
Yeah, and you have the MA for outboard word, and you put the one for store word up before, and you
Yeah.
have this. So as long as you understand those for
Yeah.
that question, you'll be fine.
Yeah.
But it's like the input and output of a certain mux. I might like
Oh, so
Because on like the homework, it said like be careful and not like include.
include too many muxes.
yeah, so let's do the muxes, right? So if
Yeah.
you have muxes here,
Yep.
Oh, are we deleting all that?
you're probably right.
You probably, yeah, and then upload that.
But it's recorded now. It's recorded in the Zoom.
True.
Yeah, and it will be in the recorded links, and you can go see it there.
Yeah, but
Okay, I'll save it. I'll save it here. I'll open a new one.
I'm not like opposed to it, but just.
No worries.
That's not-
So No worries. So
I mean, I'm gonna put the chart on my sheet, which has like the mux values for each cycle, like
Yeah.
like where it says low word, store word, and it says 101, like all that stuff. But I'm just saying, like tracing on the actual path for certain instructions might be a bit tricky. Again,
Okay,
I know we
which-
don't have to do that exactly, but I don't know the type of question that might need that.
Like, given like the homework question, or how we had to like go through, like, in order for us to understand, like.
Like for
Yeah,
either
we're
for
just
single
going through,
cycle,
like,
but
how
not
do you
multi-cycle.
trace
Yeah.
So, okay, so let's take an instruction, R type. So for R type, what happens? PC is being read,
Mhm.
and the instruction, the mux select line is 0.
Mhm.
It gets the address is assigned to the memory. The memory reads from that instruction,
Yeah.
from that space, and then the instruction is popped out here. It gets stored in the IR
Yeah.
And that's
Right?
fetch.
for fetch. Yeah.
When can we, input to the control to generate the opcodes or whatever? Not the opcode,
ID.
it's your ID.
Yeah, but we will cover. We've already covered that in the other lecture. But so, all right. So PC is being read to the mux, and the instruction is stored here. Simultaneously, once PC is read, what happens? PC goes here to this mux.
Yep.
4 from this mux. You add PC plus 4
To get the next register.
to get the
next address.
next address.
You
And-
jump to the 4 again for like, wow. Why did you jump to 4 from the mux?
Because you increment every
Because
time.
you're gonna have to do.
Oh, PC plus 4, so
Right,
that's 4,
yeah.
plus some 0.
You increment after every
This-
instruction.
You're going to actually do what you're at.
Mhm.
This is making it preset so that the next one is already in go.
Okay,
So
okay.
you're doing it the same, it's,
That's why it's-
from what I'm understanding, it's like, you're introducing pipelining. You're doing like two things at the same time, kind of. Or building up to it.
It's happening almost concurrently, right? It's not pipelining per se, but pipelining meaning what is that like I gave the example here, right? So
I don't know if I'm confusing pipelining with multi now,
no, we haven't talked about pipelining at all.
but you talked about it like before we even did single.
I gave you the example using the
Yeah.
planting a tree, right? But that's for pipelining. This is not a pipelining at all. Pipelining meaning what happens is pipelining. Oh, sure. Okay. All right.